Stuck. All right, listen. I wasn't here yesterday, and you guys did a bunch of examples. Look, there's a lot of homework over there. Not all of that's for you. Only the stuff that's in green. And what I'm going to show you today is how to do these same problems shorter. So we don't have to write out 50, 60, 70 electrons, 70 arrows, 100 arrows. Nobody wants to do that. So I'm going to show you how to do that. All right. I'm sorry. My bad. That's tomorrow's class. I'm going to show you how to shorten them up. Today, I forgot. You guys are actually behind a little bit. You have their class had a double today. You only have a single. I'm going to show you today how to write the electron configurations correctly beyond a certain point. I didn't give you anybody past calcium. I shouldn't even have given you calcium. All right, because it turns out that things don't happen the way you think they will. Things go a little crazy. Let me show you with an example here. Watch. I'm going to just try to do a large element like, I think strontium would be a good choice. All right, so here's strontium over here in the periodic table. Okay, he's got 38 electrons. And you might think to yourself, well, I could do him. We've already done about 10 of them. I had 10 of them on the board. Yesterday, you probably worked on them and got them all done. Thought, well, there's nothing to this. But if I had chosen strontium, you would have done him wrong. And let me show you why. All right, here's what you probably would have done. You probably would have, hold on. You probably would have done this. You would have said, okay, strontium's got, what did I say, 38 electrons? Yeah, 38 electrons. So you would have said, okay, 30, I got to take care of 38 electrons somehow. I'll start with where the first one's going to go. Don't do this, by the way. This is not to be done. This is just showing you how you would do it wrong. Okay, so you don't want to copy this down, just confuse you. What's the first thing you would have filled up from yesterday? 1s. Everybody agree? 1s. You envision an empty atom. I throw some electrons into an empty atom. They're going to go to the bottom. They're going to go to the lowest energy level. And the most stable, the only shape in the first energy level is the s. So 1s2. After the 1s fills, it's filled up. There's no more room in the first energy level. There's only one shape there anyway. The second energy level has two shapes. He has the 2s, which would fill up first, and he has the 2p. Okay, so that gives me 10. But I got 38. Next one, is there a 2d? No, there's only 2 in the second energy level, so I can't go to the 2d. Second energy level is filled. I'm probably going to go to the third energy level, and I will. So I'll go to the 3s, and I'll put a blank here, and I'll draw him in there. And you think, oh, I'm going along real well, real nice, okay? After the 3s fills, what would you think would fill next? Third energy level has 3 shapes, right? S, what's going to fill next? Anybody? Yeah, I mean, if you're forgotten, you can look at this little summary board over here. You know, the 1s, 2s and 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So 3p would probably fill next with 3 blanks and, okay, 6 electrons. And then you probably would have said, I'm going to leave out the arrows from now on. After the 3p fills, you've still got the 3d to fill. And then it would go and fill the 4s, the 4p, 4d, 4f. And it would be nice if life were that simple, but it isn't. Unfortunately, that's not what happens. After this point right here, things don't continue the way you'd expect them to. Electrons do not go into the orbitals that are in the lowest energy levels first, even though you would think they would. And the reason for that is the shapes of the orbitals are different stabilities as well, different energies to them. Turns out the S shape is the most stable. That spherical shape is very stable. Compared to the P, which is less, the D is even less than that, and the F. So that, let me explain. If I have an atom, and here's his energy levels, okay? You might think if I throw electrons into an empty atom, they're going to all fill up the first, and all the second, and all the third, and all the fourth, but it turns out once you get to the third energy level, I'm leaning against it. There's 1 shape in there, there's 2 in there, there's 3 in there, and there's 4 shapes in that one, right? Well, things go well until you get to the third energy level. And then it turns out that the 4th energy level's S shape is actually more stable than the 3rd energy level's D shape. So it will fill before that. Let me show you how the actual order goes. After 3p, instead of, again, don't write this down. I'm going to give you the actual rule and everything else that governs it in a minute. If it seems confusing, it should. After the 3p, the 4s fills, and then the 3d. And then after the 3d, the 4p fills. You might say, well, is the 4d next? No. Then the 5s. And how are you supposed to remember this? Because it all kinds of goes out of place. Well, the good news is you don't. I'm going to show you a trick where you could where you don't have to actually memorize this, but you're actually going to have a little device that's going to help you predict the order that these guys go in. They go in order up to a point, and then they go a little crazy. Well, I'm going to show you how you can predict the order of all of them right now. Okay? 3 rules. And the first one is the one that's going to do it for us. It's going to predict this for us, called the diagonal rule or the Aufbau Principle. These are kind of 2 different things saying the same thing, but in different ways. One's a trick, and the other one's the rule. I'll explain. The Aufbau Principle basically says the electrons are going to fill up energy levels that are, they're going to fill up orbitals that are of lower energy than first. The weird part is the lowest energy orbitals aren't always in the lowest energy levels. Okay? And the diagonal rule is a little trick that allows us to predict the order in which they fill. Okay? So, let's say that again, because it is confusing. You ready? If I throw electrons into an atom, they're going to go to the lowest energy orbital. They're going to go to the place of lowest energy. However, that place isn't always closest to the nucleus. It isn't always in the lowest energy level. Because the shapes are different energies, because the shapes, some are more stable than others, a shape that's further away, the S shape, actually tends to be more stable than an inner D shape, all right, and F shape. So write this down. Electrons fill lowest energy orbitals first, but they are not always at the lowest energy levels. That's the principle. The diagonal rule is a trick to help us remember it and not have to actually memorize the order they fill in. So I'll show you the trick next. Here's the trick. It's just a device to be able to use to tell you the order they're going to fill in. Because remember, you're not going to keep going 1s, then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. It doesn't go in order, and it gets kind of weird, especially after 3p. So here's what I want you to do. I want you to just write down all the existing orbitals. Okay, so we'll start with 1s. Underneath that, we'll put down the second energy level. How many shapes are in that one? 2. The 2s and the 2p. And make sure you line up all the s's and all the p's as I do this. See what I'm doing? I'm just lining them all up. So if you can count to 7, and if you can remember S, P, D, and F, which is all you'll ever have to go to, then you can do this rule. Okay? Now the 5th energy level should have, by rule, how many shapes? 5. Problem is, we don't really know because we run out of electrons by then. There's no real 5th shape there. We don't really know what it would possibly be because we don't have enough. All the known elements are taken care of by then. So we just keep writing the same thing over and over again as you go down. And that is called, well, it's nothing yet, but it will be called the diagonal rule when I do something to it, which you're going to do in a second. Okay, now it's called a diagonal rule because you're going to take a diagonal arrow and you're going to draw and move the head of it over one space each time, and it will tell you the order in which these guys will fill. Don't try doing it with me. Wait till I do it all the way through so you see what I'm doing, okay? Watch. The first thing to fill, you take a diagonal arrow and you draw it like this. The first thing to fill is the 1s. I move that over one space, then the 2s. I move it over one space, 2p, 3s, 3p, 4s. All I'm doing is moving this arrow over each time one space. And that's the diagonal rule. This tells you the order in which they fill. Now you can draw that over there. And once you've drawn that, you no longer need this summary chart over here. It's useless to us. It's completely useless. Because that tells me the real order they fill in. So I'm going to leave on this board over here until the test comes around. I'll draw the, so we can refer to it, I'll draw this same thing, the same diagonal rule over there. Now let's see if we can put that into practice though first. I'm going to do an example. I'm going to do gallium. He's got 31 electrons. That's way past the number of electrons where things start going a little crazy. Okay, so let's do gallium. I'm going to leave that down below as a reference for us, okay? Now, you need to write small. I have a hard time fitting gallium on this smartboard, all right, in order and for you to also be able to see it. The writing's a little too thick. You need to start way over to the left, as an example of this one, and write down gallium, Ga. Gallium has how many electrons? 31, I believe.
Oh, 31, sorry.
It's all right, 31 electrons. Now, underneath him, and starting far to the left, because it's going to take up 31 arrows you got to fit across. Let's start filling these up using the diagonal rule. What's the first thing that's going to fill up? Look at the diagonal rule, 1s. It's not memorization. Just look at the rule. After the 1s fills, what fills next? Take a look at it. 2s. I'm writing small, and you should too. I still may have trouble fitting all this on here, because it's all got to fit on one line here. After the 2s fills, take a look. 1s, 2s. What's next? 2p or not 2p? That is the question. Apparently, Shakespeare had a microbladder. 2p or not 2p? Okay. I've taken care of 10 of the 31 electrons. What fills after the 2p? 3s. Good. After the 3s fills? 3p. After the 3s, back up to the 3p. 3p has 1, 2, 3 blanks underneath them. 1, 2, 3. They go in one at a time. We're going to call that Hund's rule in a second. There it is. Now, if you were to not be using the diagonal rule, you'd be wrong, because you'd put 3d next. But now you know. It's the 4s that's going to fill next. And I've taken care of quite a few electrons. I'm not quite there yet, though. Let's see how many I've got. 10, 20. I got 20 taken care of so far. I need 31. Where are the ones that are going to go after the 4s? The 3d. Now, 3d, I got to put how many blanks underneath the 3d? No, 5. 1, 3, 5, 7. Remember that from last week. And that's going to take 10 electrons. That's good. We're almost there now. Almost there. Because I can fit 10 electrons in that guy, can't I? After the 3d fills, again, no memorization. Use the rule. After the 3d fills, 4p. How many fit in the 4p? I'm sorry, how many blanks go underneath it? 3, because all p's have 3. And then?
1 arrow.
1 arrow. Only 1 needed there, because that gives me a total of 31. And that's how many I wanted for gallium, and I'm done. Okay? And that's what gallium would look like. Isn't that nice? All right. Now, that pretty much just illustrates for you how you're going to use this rule for the rest of the chapter and whenever you do these, for the next couple of chapters. All right. That's called the Aufbau Principle, or the diagonal rule. We are going to use that to do any of them. There's a couple of other little rules I want to show you today. Next one's called Hund's rule. I've already been using Hund's rule, and so have you. I told it to you. I just didn't have you write it down at the time. We were kind of short on time, and I wanted to give you all the rules at the same time. Hund's rule simply says this. Electrons, and you've already been doing this, I think. Electrons go into orbital blanks, orbital positions, sublevels, one at a time before they go back and pair up. Okay, electrons do not pair up in any set of orbital positions until each position contains at least one electron. And I could use as my example of this, although it could be illustrated by almost any atom. I think it's illustrated very well by nitrogen. Nitrogen has a total of how many electrons? If you look at the periodic table, he has 7. He has 7 electrons. So I got to fill up 7 electrons. Now, again, I can go back. I don't think we need to. This is such a small one. We all know what order they're going to fill in, right? 1s is going to fill up first, right? Everybody good with that? Then what? I mean, you could use the diagonal rule, but really don't need it yet. It's 2s after that. And I only need 3 more electrons, and they're going to go into 2p, correct? But how will they go into 2p? Well, that's what I told you very briefly last Friday. You would not do this. That would be wrong. You don't have one filled, one empty, and one half filled. For whatever reason, electrons don't like that. They're not stable that way. They would be happier going in one at a time before they come back and pair up. Okay? So that would be the correct answer up here. This would be wrong. Got it? That's Hund's rule. Very simple. Made by Attila the Hun back in the Mongol. Not really. Dynasty. Okay. The Octet Rule is the last rule, and then I want to just show you something that people have been asking questions about. Has to do with electron dot notation. Okay? Yeah. As soon as we're done. I'm almost done. Okay, the last little thing I've got for you is the Octet Rule. And really, the Octet Rule is not about this chapter very much. But it is really important. It's probably the most important thing from this chapter you're going to take. Because it predicts everything about atoms that we want to ever know. Okay? Don't have to write this down. Just let me show you something. Why is water H2O? Why is carbon dioxide CO2? And why is salt NaCl? I mean, why isn't it Na2Cl or NaCl3? Why? It all has to do with the Octet Rule and the configuration of the electrons for the different atoms. This rule is going to be really important next in every chapter from now on. Whereas we will only be writing these kind of notations out maybe one more chapter, we'll be using the knowledge of them forever and basically summarizing it with the periodic table. The Octet Rule is something we'll be using forever in Chem 1 and Chem 2 the rest of the year. All right? And that, although it's not really as important here, it will be. Here's what it says. It says atoms are happiest. They're most stable when they're filled up with electrons. The outer shells are filled up with electrons. That's what it basically says. Atoms are most stable when they have a filled outer energy level. And for most atoms, that means having 8 electrons in their outer shell, which I will also use this as a point to explain why I was going to do something a minute ago. People have been asking about the transition elements, the guys in the middle. How do you do electron dot notations? I will explain. Atoms are happiest, and you know you got to have a happy, happy, happy atom. Happy, happy, happy. Like Miss K. You got to keep Miss K happy. And those atoms are only going to be happy if they're going to be completely happy if they are filled. Their outer shells are filled. Why does that take 8 for most electrons? Well, I'll try to point that out to you in a little bit. All right, but and I say for most electrons, I should point out that there are some that are going to be filled when they only have 2. But the vast majority, pretty much everybody beyond carbon, is going to be happy with 8, all right, in his outer shell. All right? So this rule is going to govern how things react. Let me show you a periodic table. I think that's the next slide here now. Yeah, there you go. In a periodic table, if you look, we already know something. I'm going to go back to this. Remember I already told you about electron dot notations? Take a look up here. These guys call it Roman numeral 1A, 2A, 3A, 4A, and these are called B's in here. I don't even use that distinction. I just call it group 1, group 2, group 3, up till you get to group 8, which would be what? V111. Sorry. There. All right, up to get to group 8. Why does it end at group 8? Because that is, and why, for example, when we do electron dot notations, do we only have 4 sides? Because, and I told you it would never go beyond that. Well, if you look at how these guys fill, according to the diagonal rule a little while ago, okay? Whoops, I don't know how that got there. If you look at how these guys fill, turns out after you fill one, before it goes back and fills a D, it's always filling an S before that, before it fills one of these other levels, which have 10 or 14 electrons. So it turns out your highest energy level generally never has more than 8 electrons in it because it never has more than an S or a P in the highest level. Let me show you this by answering 2 questions at once. A little while ago, people noticed in the middle of the periodic table, we didn't know how to do these guys, the electron dot notations. Let me show you. Okay? Come on. Okay? These guys in the middle. People were asking, what's going on here with these guys? You said the electron dot notation is pretty easy for him. He's in group 1, he's in group 2. Electron dot notation has how many dots for group 1? 1. 2 for 2, 3 for 3, 4 for 4. Makes sense. It was easy to do. Guys in the middle, what do I do with them? They're going to have more than 8 if I include them all. Let's do a homework problem from last night. I think we had vanadium, or no, we didn't have, it's for tonight. Let's do the homework problem for tonight. So I'll be doing one of your problems with you, vanadium. We're going to kill 3 birds with 1 stone here. 1, I'm going to illustrate for you, and you can put this in your homework if you want to. I'm going to illustrate for you, as I do this, the diagonal rule again, and Hund's rule, and all the rules we just went over today. 2, I'm going to show you how you can do electron dot notations for guys who are in the middle. Okay? And 3, I'll try to talk to you about the octet rule one last time too. And because the octet rule is going to govern. Everybody wants to get 8. It gets those 8 somehow or other by getting together with another guy who we can get the electrons from or we can give electrons to. We'll talk about that next chapter. All right, but let's do vanadium. There he is. Vanadium is right here. Okay? Let's do vanadium with 23 electrons, and this will be one of your homework problems. Okay, using the diagonal rule again as a homework problem. Vanadium has 23 electrons. What's the first thing that's going to fill up? There's your diagonal rule. What's the first thing that's going to fill up? 1s, right? Everybody's good with that. After the 1s fills, using the diagonal rule, which we use in every single case, the 2s fills. After the 2s, Ronnie, what do you think fills? 2p. 2p. Becca, what fills after the 2p?
3s.
Everybody see it? 2p, 3s, good. After the 3s fills, what do you think is going to fill next, Nikki?
3p.
After the 3s comes the 3p. 3 blanks. Let's stop here and see how many we've got. We need 23. Marvin, how many do we have so far? 18? 6 and 2 is 10 and 18. We need 23. Where the next one's going to go? What do you think? Ellie.
4s.
After the 3p comes the 4s. You would have gotten that wrong had I asked this for homework yesterday. Okay, now I've got 20. I only need 3 more. Where are they going to go? After the 4s comes 3d. And how many blanks do I put underneath the 3d? 1, 2, 3, 4, 5. Okay. Do I need to put electrons in every one of those? How do I know when to stop this process? When I reach 23. And I just did, if I put 1, 2, 3, according to Hund's rule, they went one at a time before they pair up. There you have it. Now I just illustrated all the rules I just talked about, the diagonal rule, Hund's rule, okay, and the process of writing electron configurations. But I told you there's multiple reasons I was doing this. Besides that, I now want to talk to you about how I would write the electron dot notation for this guy. Pay attention. If I write down the symbol for vanadium, how many dots are going to go around it? Remember what the instructions said about electron dot notations. You only include the outer shell electrons, the highest energy level electrons. Who is the highest energy level in vanadium?
3D.
No, and that's the answer I get most every time. Most people want to say 3D is the highest energy level, but is it? This number here tells you the energy level, doesn't it? The highest energy level is not 3D. It is 4. In this case, 4s2 are the electrons that are in the 4th energy level. So this is an interesting little thing here. How many dots go next to vanadium? How many dots are in the 4s? This is very interesting and explains to me, again, why I'll never have more than 8 dots around these guys. Watch what happens. Let's do the next guy after vanadium. Let me just show you a periodic table again here. The guy after vanadium is chromium, right? He's got 24 electrons. Or manganese, 25, iron, 26, cobalt, 27. Let's see, can we do those guys? Sure, watch. Oops, all right. Okay, here's the next guy. After vanadium is chromium. There he goes, right? No, don't do this, don't do this. Here's the guy after chromium. That will make him a 5 now. Put another one over here, that makes him a 6. Do any of those change the fact that my highest energy level is 4?
No.
So how many dots do each of those guys, whatever he is, have around him?
2.
See that? Which is why you'll never get, if you find yourself putting dots like this around your electron dot notations, you did it wrong. You put them in the wrong order. Because this is the higher number, isn't it? A higher energy level. Even though here you're just filling up a lower orbital, a lower energy orbital. Even though he filled up after the 4s. Very interesting stuff. Now there are, by the way, I should say, by the way, an exception to that. A couple of exceptions, actually. I'm not going to make you memorize, I'm not going to make you know them. But I should say that in reality, there are a couple of guys around chromium and silver who, because of stabilities, we're going to learn about, I already mentioned Hund's rule, things are more stable when they are full, right? They were one at a time, I'm sorry, and Octet Rule, things are more stable when they're full. Because of that, turns out chromium and silver and 1 or 2 other guys there do some strange things. Okay? We'll talk about them. Actually, I'm not going to make you memorize them. So as far as you're concerned, all you have to know is everybody in here has how many dots to the right. And that's it. 2 dots to the right. Okay? All right.